So following on from my last video, I'd sort of talked about how, we had a special pattern that we found, which is, for any odd number of this form, if I put this into the odd Collatz function, I know because of the limits on growth and shrinking and the limits on growth in the number, that this 101 means this number will always shrink. And I stated that it was equivalent to the Collatz conjecture. I put a note there correcting that. That's not actually true. It's quite close, but it's not precisely the same thing. So I wanted to talk a little bit more about this pattern today. So in Veritasium's video, he has at one point a lovely diagram showing how powers of 2 sort of the number of powers of 2 as a total amount of the numbers diminish as you approach infinity. So, from 1 to 100, there's quite a few powers of 2, and then from 1 to 1000, there's fewer total powers of 2. The fraction of numbers that are powers of 2 out of that 1000 is less than out of 100, and that ratio, that decrease continues as you go up to infinity. But this is a different kind of thing, right? So let's consider an odd number, right, of length L. So when I say length L, I mean that, if you have a number like 10101, 21, right, this here, L is equal to 5, right? So there's 1, 2, 3, 4, 5 digits total, right? So I'm going to make my length arbitrary, and then I'm going to wonder how many odd patterns of length L do I have? Well, because this and this are fixed, right? Actually, what I have is 2 times L to the minus 2 possible patterns. So again, to take a really simple example, if you go 1 to 1 for L is equal to 4, right? I have 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, right? And then 1, 1, 1, 1. So for L equals 4, I have 4 possible patterns, which is equal to 2 times 4 minus 2, which is equal to 2 to the 2, which is equal to 4, right? So 4 possible patterns, right? And so then I want to ask, of this arbitrary number of length L, this odd binary number, how many of those possible patterns will be of this form 101, right? How many of them will have this immediate collapse built into them? And so because there are 2 additional digits here, right, where these are fixed, I can say that actually the number of possible collapse patterns is 2 times L minus 4, right? So here, to take this example, there is one particular pattern where we have this 101 pattern here, right? So let's just check the formula. So we have 2 times 4 minus 4, which is equal to 2 to the 0, which is equal to 1, right? And so if I want to ask what the ratio of collapse patterns to the total number of possible patterns is, right, I can say, well, 2 times L minus 4 over 2 times L minus 2, right? The division. Then, by laws of exponents, so that gives us, right, like the L and L cancel, minus 4. So I have 2 to the negative 2, which is equal to 1/4, right? So of any set of patterns of arbitrary length, any set of numbers, odd numbers of arbitrary length, I know immediately that 1/4 of them, from 0 to infinity for the length of this number, this binary number, 1/4 of those patterns cause a collapse in the Collatz conjecture. So, if you recall, this isn't all the patterns that immediately collapse, right? There are if you have the condition where you grow by a single number, and then you decrease by 2. So if you have your form something like this, right? These patterns of 1, 0, 0, 1. Some of these numbers are also going to immediately collapse. So it's actually greater than 1/4 of the total number of patterns. And I think in the next video, just to give you an idea, I'll run through an example where we fix our length at, say, like 6 or 7 binary digits, and we just sort of work through all of the possibilities so we can see how this works. I should note that what I'm doing here, which is sort of classifying patterns of numbers that fall apart, isn't new or original. I haven't read all the literature. I don't know all of it, but lots of other people have shown that lots of patterns in Collatz collapse. And I think like Terry Tao's recent one, like I mentioned in Veritasium's video, shows that it collapses for almost all. So I don't think this is original. I like the binary perspective because, I can sort of see it through the lens of computing, which I know quite well because of the electrical engineering background that I have. But I just think this is all sort of neat.